Next up, we have scaling Thanos infrastructure dynamically with Sharad.
Okay, I'll be talking about how we scale a Thanos metrics infrastructure based on user needs. Like whenever our Kubernetes cluster scale, how we gonna do it? Okay. Intro. My name is Sharad Gaur, and I'm based out of Atlanta, Georgia, working as a production engineer in observability team from last almost 3 years. Um, hobbies, like to play games. If anybody play video games, raise hand. Damn, no, that's good team. Uh, do outdoor boring stuff like camping, hiking, nothing much. Uh, so I would like to start from 1,000-foot view of our metrics ingestion pipeline. I think already Philip covered it, Sam and Andre covered it. So you can imagine we have Prometheus infrastructure running in Kubernetes client clusters, and these Prometheus are responsible of collecting metrics from that cluster. When I say client clusters, I mean where Shopify infrastructure is running in. And these Prometheus send metrics to metrics ingestion pipeline, which is routers. Routers, you can imagine like a smart load balancer, which takes the config and spread those metrics on the receivers. Receivers are nothing but TSDB. So if you look at it this morning, we manage Prometheus agent using custom Prometheus operator built by Sam and Andre. And these operators are smart enough. Whenever flash sale happens in production, Shopify service scales. Whenever Shopify service scales, Kubernetes cluster scale. Whenever Kubernetes cluster scale, agent scales to handle that load. And when agents scale, we have to scale routers. Routers are scaled by HPA because they are stateless. We just know by CPU how to scale up, how we need. So in this talk, I'll be talking about how we scale Thanos receivers. Everything after that, Philip is already covered. So before I go in receivers, I want to give a little bit background about each of those components. So router is nothing but receiver image. If you look inside the code, only thing it does, as name implies, routing a matrix, replication, hashing algorithm. And all these three information is supplied by hash ring configuration, which typically look by tenant name. Whenever I send tenant, it's the Kubernetes cluster name in our use case. So it's just tenant name and how many receivers we are going to spread those metrics on inside the receiver pool. And so if I walk you through the Prometheus agent, so Prometheus agent gonna remote write a metrics payload with the header of tenant. Router will receive that payload. It will read a tenant name from the config map. It will figure it out, hey, all these endpoints I need to spread metrics on. It will read each metrics series, run a hash mod on it, divide by mod by number of endpoints, and stick this metric to the particular index, particular receiver. And that's what it does. There are two hashing algorithm, Katama and simple hash mod algorithm exist today in router. So as you can see, router is mostly in-memory processing, stateless kind of thing, so it's easy to manage through HPAs. Thanos Shard Manager. This is our in-house component. In Shopify, we boot Kubernetes clusters, shut down Kubernetes clusters daily. We're not gonna manage those hash ring config manually inside GitHub. So what Shard Manager does, it constantly discovers new Kubernetes cluster every 5 minutes or so. And once it discovers a new Kubernetes cluster, it updates the hash ring config with that new Kubernetes information. It adds a new entry. It also aware of how many receivers are deployed, replica, And based on that, it randomly generates default number of shards and update the endpoint. So shard manager just constantly updating this config map, and this config map is used by a router. And router, when metrics received from this cluster, is ready to handle it. Receiver, one of the most important component in our metrics ingestion pipeline. You can imagine receiver is, you can visualize it like multi-TSDB. When I say multi-TSDB, one receiver can host multiple tenants. And these tenants are nothing but Prometheus booted up in memory. Each of these Prometheus, by default, is configured to store, produce block of memory every 2 hours. In our case, we are doing every 1 hour. So that means Prometheus hold the metrics for 2 hours in memory. There is nothing on the disk. It will produce after 2 hours on the disk. Receiver, TSDB, they store 6 hours worth of latest data. So when I say 6 hours, that means when you open a dashboard, and if your dashboard is default to 3 hours, that query will be received by a receiver, nothing else. If you change the range, time range to 12 hours, 6 hours will be received by receiver, and then last 6 hours received by Parquet stores. And you can do the math. If somebody fired a 1 hour query, 1 year query, 6 hours gonna be received from receiver. So receiver mostly receive all queries. And receiver is in critical path for alerting and everything. So all alerts, all SLOs are fed by receiver. So you can imagine we don't want downtime of receiver. So initially, we created a static pool of receiver. So in each region, we have 200 plus receivers running, and that's it. We cannot manage by HPA because of their stateless nature, stateful nature. And yeah, so what we did to manage tenant on those receivers, we built lots of tooling around. So we have a tooling where you can move tenant from one receiver to another receiver. So when I'm saying moving tenant, technically you can imagine we are updating hash ring config and updating IP address into endpoint list. You can flush the tenant. You can force receiver to flush block on the disk. That means we can say, hey, don't wait for 2 hours, just produce a matrix on the disk as a block on my demand. And you can compact whenever we want to, like we want to free up the tenant, free up the receiver, we can run a compact on that receiver, which will distribute all the tenant of the receiver to other receivers and free up that receiver, and we can shut it down. And we have, these toolings are perfect. They work most of the time, help us to manage it. But imagine, in middle of night, I got on-call page, hey, there is a receiver in US East going out of memory. So what I'm gonna do, I'm gonna wake up, go downstairs, open computer in bright light, and I'm gonna check the dashboard. Hey, receiver 16 is going up there. I will check the tenant out of it. This tenant is, eyeball it, abusive. And I'm gonna say, write a command, remove tenant out of receiver 16, move it to some other receiver. As soon as I press a command, I realize it was 15 because I was seeing blur at that time because it was on. So imagine if the chances of human error was big, even though tooling is good. These commands, they don't manage receiver state. Like, what if the tenant is so big, we need to add new replica for receiver? These commands only can move within existing replica those receivers. So we have to do CI. We'll create a PR. I'll post a PR into Slack channel. I'll hope somebody middle of night will approve it. If it is not, I'll do emergency merge or some hack and deploy it and wait for CI to deploy successfully over there and then run those manual commands. By the time you already have an incident in your hand, entire team is already in Slack channel, and we have a meet group going on. and everyone blaming what the heck, Sharad, you did. Uh, so other issue is, like somebody asked, hey, tomorrow we're gonna do BFCM scale test in, let's say, US East. And we'll say, okay, yeah, good. And they'll say we increase 40% of our workload over there. How many machines you need? Because the way receivers are managed by memory, we have hard time determine, do we need more receivers to handle that much load? Do we not? And I can give you an example on it. You see, this is one of the regions where we have 230 receiver pods. Min memory utilization is 20 gig. Max memory utilization somewhere 90 gig. If somebody say 40% jump, what I'm gonna do? I'm gonna add more receiver because I don't know 40% from here or 40% from here. I'm gonna add more receiver, that's wastage of money. And you can see there is a big uneven distribution of memory. Entire Colorado River is flowing in here. So nothing going on. So, what is the solution? Rather than reactive management of infrastructure, when I say reactive, whenever I'm watching dashboard, whenever I got alert, we start fixing that thing, we need to be proactive. When I say proactive, that means we should build a system which can take accommodation of whatever the receiver maximum memory is utilized, and based on that, it can move tenant, it can even add replicas, it can even scale down when we don't need that system. And that can happen seamlessly without human intervention. So, as you can see, moving a tenant means, in visual sense, moving a tenant to another receiver, but behind the scene, it's just updating hash string config map. So we came up with the simple criteria to do this thing. There are several ways you can achieve this thing by, you can make it complicated. You can have 15 input commands just to make it this management, but we want it to be simple. So we want it to be simple enough that we can calculate what automated system gonna do rather than it become magic. So as a team, I figured out how we are comfortable with receiver memory utilization. So as a team, I think we were comfortable, let's say, receiver memory utilization 60% or below, we are comfortable. If it goes above, we are in panic mode. So that's the input for this. If any receiver takes more than 60% memory, what this tool does is automatically will figure out which tenant is abusive in that receiver. And if we move those tenants out of this receiver to another receiver, does that receiver also crosses that 60% threshold? If it is not, move that. If it is, try to find other receiver. If it is not, add the replica and assign it. And if all receivers are below 60%, try to scale down all the time. Remove all the tenant from last replica, try to assign it to all other receivers. If they can successfully can be assigned without breaking 60% threshold, yeah, do it, shut it down. So scale down. But the challenge was how to determine the potential memory impact on receiver when we add or remove tenant without doing that change in production. And you think, why can't you figure out this part? The reason is, we know how much memory receiver takes because it's a pod. You can get C advisor metrics, container memory working set byte, you know total. But one receiver hosts multiple tenants, and they are in memory. We don't know each of those tenants, how much memory they are taking. So we have to come up with some math. So what we know, each of these tenants, we have a matrix called Prometheus THDB head series. which tells us how many head series Prometheus is holding. By the way, we added this into Prometheus. Um, so we can use this metrics to calculate per tenant number of head series. We can also sum all the head series of all the tenants within the receiver to get total number of head series hosted by receiver. And once we have this information, we can use simple mathematics to estimate the total memory used by individual tenant. So receiver pod memory utilization divide by total number of head series hosted by that receiver. So we get per receiver, per series memory utilization. And if we multiply by tenant head series, we have per tenant how much memory they're using. It's kind of like a pie chart. We know each of these we use. Now, since we have this thing, now only thing is that we can just compare. So what we do, if receiver goes above 60%, we remove a tenant. Hypothetically, we are not removing physically. Right now, we are calculating. We remove the tenant. We see receiver memory goes below 60%. If it is not, remove another tenant. If it goes below 60%, we know these are the tenant. It can be removed. But next question is that, can we move these tenant to another receivers? So we goes to the sort by memory, least memory utilized tenant. We try to add these tenants into that receiver. And if that can added, it's good. Apply the change. If it is not, scale up. Add replica, apply the change. So I want to show before and after we implemented that. This is a receiver memory distribution before with Colorado River. You can see 230 receiver. Their min memory utilization was 20 gig, max was 80. After we reduced 40 receiver, min utilization gone up to 24 gig, maxes went to 48 gig. And you can see these are over here. There are few receiver crosses the 60% threshold line, and our operator did whack-a-mole kind of job and moved this stuff out. You want to see some scale up? Background on this particular chart, we were not aware there was a flash sale going on in one of the region. And it was so big that Kubernetes cluster scaled crazy fast. Same thing, Prometheus agent scaled. And because of that, you can see all the receiver in that region gone up. And you can see up here on the bottom where the arrow is, there are new receiver popping up and taking a load. And if you check the spike, it's hundreds of GB extra data coming in. And it's technically saved us an incident. And you can see over there, once the receiver done their job, this L-shaped chart is telling they are scaling down after handling the load. Imagine if there is an incident happens, if we didn't have that, by the time we get page, it's already too late. We're gonna have full-blown outage. There is another chart. It's a number of node count in that one region. There was 200 node, and you can say staircase. So we want scale down slower, but scale up faster. So you can see all the time whenever scale up is a vertical line because we add multiple receiver at the same time. But when we scale down, we make sure we didn't do any kind of scale up before scale down. So wait for 3 or 4 hours when we start scaling down. And that's why you're seeing staircase kind of pattern over here. So majority of time we take 190 nodes, but sometime we have to jump to 220 to accommodate the need. So it's a liquid kind of infrastructure. Q&A. This is ChatGPT. Sorry, I didn't come up with it.
Okay, so when you're deciding what tenants to remove, are you choosing them randomly, or are you looking for the individual abusive? How are you figuring out which tenants to move around?
So there are two strategies. Either you use the small tenant, but the problem with the small tenant, that change gonna be big. We have to move lots of tenant. So we are choosing the abusive tenants because we want less change inside the hash string.
First, I trust you 100%, but when you
No, you don't.
when you did the migration, did you build any guardrails, or do we still have guardrails built in? So if something goes wrong.
So there are certain guardrails built into it. So since this system is totally based on metrics, and these metrics is collected by Meta Prometheus, so we make sure we have metrics for each of these receiver before we do any change. If metrics is missing, we're gonna skip. We're not gonna do any change. Second thing, we added max replica and min replica of the receiver. So we don't wanna be scaled down to, let's say, some outage happen in Shopify level, and we scale down to one receiver in one region. We don't want that kind of thing. So we have those min replica set. And in last slide, that 190 default number, this is min replica. So we are not gonna go below that. And it's up to us as a team. If we see tomorrow, we can scale down more. So we can change min replica, so let's say 160, and system will adjust accordingly.
I speak for the whole metrics team. Thank you. And I'm just curious, given that if you made a mistake here, you would have caused an outage.
Big time.
Yeah. Just tell me about how you were feeling deploying this.
Nobody in our team was comfortable. That's what I can, even me. I was working on this project, but I have to give credit to Matt. He pushed us to go in this direction. We were not comfortable of making receiver this elastic. And I was scared to death when I was deploying this thing in each region. So, yeah.
Yeah, I remember we turned it on and off before this multiple times.
Yeah.
So how do you scale out stateful replicas without losing data like this?
So scale out without losing replica. So what happened whenever we identify an abusive tenant, and if we cannot move it to any existing replica, I'll add a new one. I'll wait for, I'm gonna say, the system will wait for that replica to come up successfully. Sometimes GCP take time to boot up that thing. Once that get boot up, I assign that tenant to that replica, and I flush out the tenant from previous replica. So that block get produced on the disk and get uploaded. So there is no outage in that case. Yeah. When we scale down, we have to worry about losing data. So we make sure when all the tenant get removed from that receiver, we're not gonna delete that receiver until 3.5 hours later. So by the time no new metrics coming to that receiver, and since we have a 1 hour block, we already all the data is already get uploaded to GCS. So we have a buffer of 3 hours.
Hey, my question is about the math part. So you talked about calculating like whether a pod is, or a receiver pod is above that 60% threshold, like memory-wise. And the calculation seemed like so simple to me. And I've looked at that calculation before, I think only on vanilla Prometheus, and I could never isolate out like what part is the storage of the series and what part is the querying of the series or other operations that consume memory. So how is it that in this case you're able to make that calculation so simple and just like, I guess, isolate that storage?
Yeah, that's a good question. So that's why I call it estimate. But it's overestimation, because every time when we calculate that simple, we are taking in count, it's not just series, we are taking THDB creation take some extra memory, maybe some query buffer is taking some extra memory, that get counted also. We wanna estimate over rather than under to make this work.
Thank you.
Thank you.